Hello class, welcome to lesson 21 of our Acme course. Here we are going to talk about trees and forests, and that means regression trees, classification trees, and random forests actually. Here are all the packages I use today. So first of all, let's start with just some basics of decision trees. So the concept of decision trees is very straightforward. You start at the top and then you down by making a series of yes or no decisions to certain questions. So let's say here, for example, we are classifying animals tree. The first question we ask is, does the animal breathe air? Then either yes or no. If we say it does not, then we say it's a fish. If we say it does, we ask the following question. The following question is, does the animal lay eggs? And then if it says no, we say it's a mammal. And if it says yes, we say it's a bird. And yes, I know that's not accurate. There's also reptiles and stuff. But for the sake of argument, let's say this is a decision tree. That works. So this is how all decision trees function. And this principle is at the basis of all these very powerful machine learning techniques that we're going to talk about today. Let's talk about tree anatomy a little bit, or just vocabulary that you need to know. So the squares here in the tree are referred to as nodes. The top node, this one right here, the first question we ask essentially is called the root node. Um, these other nodes here in between are called intermediate nodes or decision nodes, or you just call them nodes. However, these end ones, the ones that are in red, those are called leaves, obviously, because if this is a tree, then these are the leaves of the tree. And the different paths you can take through the tree are often called branches. Now, if you don't think of this tree as just being a guide for decision making about one uh, observation, but rather as a way to split your sample into groups, then what you see is that at each node, sample gets split into two groups, the yes group and the no group. So the tree we just saw a second ago, that was a classification tree. We were classifying animals into types of animals. In other words, we were using a categorical variable and we were assigning a category to observations or groups of observations. Now, a regression tree does something similar, but using a continuous variable. And we don't assign a category, we assign a value. The algorithms that solve regression trees are a little bit different than the algorithms that solve classification trees. We'll come back to that. Regression trees are based on minimizing mean squared errors, similar to regression lines. However, classification trees are based on minimizing something called impurity. We'll talk about it. If you try reading up on this a little bit on the internet, you will often see the word CART. CART just means classification and regression trees. It's not a different technique, it's just a word for all of this stuff that we're talking about today. So let's start with the regression trees. And let us start with just an example. Let's do a regression tree in a bivariate setting. Bivariate setting, I just mean that we have one x variable and one y variable. So we are just trying to predict y using values of x. Let us make some fake data. We're going to have 17 observations, and x is 1, 2, 3, 4, 5, etc. until 17, so all of the integers. Y, on the other hand, is also integers, but with these numbers. I'll plot them in a second, you'll see them. So let's make a data frame and plot them. This is the data we have. So as x increases, y first increases linearly, then it kind of jumps up and down here up at the top between 7 and 8. Between 8 and 9. And here then it goes down to 5 and then down to 4. Clearly fitting a regression line through this data is not perfect. This is a rather poor approximation of where the observations are. It does capture the general upward trend, but other than that, it's not a very good predictor. So what we would like instead is an algorithm that can allow us to recognize the fact that actually this data is kind of bunched into different areas. There's a group of points here, there's another group of points here, and there's a third one here. Visually, we can recognize them. Regression line does not allow us to do that, but the regression tree is going to allow us to do exactly that. So what a regression tree is going to do for us is that it's actually going to split the data into these three zones. These three zones are defined by the range of x, not the range of y, even though they actually define groups in the xy space. So let's say here's a first zone that is below this red line, somewhere between 5 and 6, that defines a group here that has y values 1, 2, 3, 4, 5, mean is equal to 3. Then there's the second group between these two lines where the mean is 8.5. That oscillates between 8 and 9. And finally, here's a third group with these 6 values, the mean being 4.5. So the splits are defined simply as vertical lines here on the x-axis. And how does that map into a tree? Well, it maps because we can think of them as successive splits. So the first split is answering the question, is x less than 6? And if it is less than 6, then we're in this group where the mean is equal to 3. And if it's greater than 6, then we're in that group. And this group gets successively split another time into 2. And if we are below 12, we're in this group at mean 8.5. And if we're above, we're in that group with mean 4.5. These splits, by the way, define a full partition of the x space of our prediction variable. So importantly, in each leaf of the tree, we are using the mean of the observations in that group as the predictor for our whole group. So this can feel like it is a little bit crude, but don't worry, these predictions will get better as we move along, you'll see. So I found this funny visualization online from this publication here. I'm sure you've heard of the story of the 6 blind people who were trying to know what an elephant must be like. And because each of them only has access to a part of the elephant, it is not able to really have a global view of what the elephant actually looks like. Well, that's kind of what we are doing with these regression trees. We are bunching parts of the elephant that are kind of similar into a group and that or into a leaf in that case, and each leaf is represented by its average. So our tree finds parts of the elephants that are kind of like each other and gives a crude prediction for each of those parts. So the first question many of you might already be asking is, why did we not continue splitting? Why did we just make 3 groups? Could perhaps yourself see smaller groups that we could that that made sense to you? Well, yes, and you could do that. And in fact, you could actually continue splitting until you would only have one observation in each leaf. And once you have that, actually, well, then you have a perfect fit. You actually perfectly fit your tree to your entire data set. Of course, you're starting to get familiar with the problem here. That would be overfitting, right? Because then every single x value would be predicted exactly by the value of y of that data set, exactly the way it is, which is very likely not to translate into any other sample, even if that sample was drawn from a similar or the same population. So how do we avoid overfitting in regression trees? Well, the simplest idea, the first idea you may have, is to say that we can set a minimum number of observations per leaf. So the second question you would ask is, okay, now how do you actually determine where to split the x-axis? Where are the actual thresholds? We could see them visually, but how does an algorithm actually see them? Well, the way it's doing it is actually by testing every possible split and then picking the split that has the lowest mean squared error. The mean squared error being the same one as we have in regression, the difference between the actual value and the predicted value squared and summed. So it does that one time trying to find every single split and picking the best one for the top node. Then inside of these 2 nodes, it does the same thing, trying every single split and splitting again, trying every single split and splitting again, etc., 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 until it reaches the lowest possible leaf in each of the branches. So here's concretely how that would work exactly on the data set we have. So trying to first just find the first split, the root node, and assuming that we don't have any minimum number of observations per leaf, the algorithm would go as follows. It would compare all possible 16 splits. So there are 16 possible splits because we have 17 observations. So you could cut between the first one and the second one, or you could cut between the second one and the third one, or you could cut between the third one and the fourth one, etc., etc. So it tries at each each possible split, it tries it for all 16 of them. I'm only showing 8 here because otherwise it would be impossible to read. But for each of these splits, what does it do? It computes the mean squared error, the total mean squared error. So what is the total mean squared error? It's the mean squared error in the subsample on the left and plus the mean squared error on the subsample on the right. So on the left here, we only have one observation. So the mean is 1 and the mean squared error is 0. But here in that subsample, we have 16 observations. The mean is 5.47, and it computes the mean squared error here in that sample. Then, here this is MSE equals 0, MSE equals 104, so the total MSE for this split is 104. Then here it tries again splitting here. Here now we have 0.5 as the MSE. Here we have 83 as the MSE, so the total MSE is 83.5. Then the third split, MSE is 70, the fourth split, 63.36, the fifth split, 63.08. The sixth split, it's 81. We're going back up, we're going back up, we're going back out. I'm not showing them all, but they actually keep going back up. And so this is why this first split is chosen as the best one, because it has the lowest mean squared errors among all of the possible splits you can do out of this sample. So as you see, unlike a linear regression, which has an analytical solution and is based on matrix inversion, here we don't have an equation to solve. We actually by hand go and look for the lowest mean squared error. Of course, when you run the algorithm, that's all automated, but in the background, that's what's happening. And so that's how you find the first split, the root node. The root node is then going to be this split. And then you repeat this same algorithm inside of each of the subsamples that you've defined by this split. And that's how you obtain the tree with the 3 leaves that we had at the beginning. So right here, we just found this separation between 5 and 6, 5.5 it was. This corresponds to what I informally put in this tree. This is our root node. X strictly less than 6 is this separation. And then we would do the same thing and we would find that second one, assuming that you're also preventing the tree from going all the way down and splitting into 17 different leaves, right? Now you might ask, what does that look like when you have 2 predictors instead of 1? So let's say now you're predicting y as a function of x1 first predictor, x2 second predictor. Again, what the tree will do is it's going to try every possible partition of x1 and of x2, and that's going to define 2 subsamples, and then it's going to look for the all possible partitions of each of those subsamples, and then it's going to find the best partition. And then in those subsamples of those subsamples, it's also going to look, etc., etc. So you see how it goes. Importantly, at each split, it tries on both variables again. So it tries all the possible partitions on x1 and on x2, and it decides that the one that reduces MSE the most is x2 less than 0.03 here. So this is the best possible split we can have on either x1 or x2. Then within these two groups, it tries to look for another split, but again, it tries that split either on x1 or on x2. And in this case, the best split is a split on x1. In this case, the best split is also a split on x1. However, as you see, here you make another subgroup, and we're still continuing to split on x1, even though the x2 splits are also tested. It's just that they're not the ones that reduce MSE the most. Until we get to this leaf, where x2 again, which, by the way, was already used up here in the first node, it is still reused here again to create this last node. So there is no particular ordering of how we have to split. There's no particular number of times we have to split on each variable. None of that is constrained. So now if we look at our x1 and x2 variables, so you imagine this is the floor of a 3D space. This is our x1 variable, this is our x2 variable, and here the colors are the value of y, let's say. And here you see the tree, each of these boxes represents a leaf of the tree. So this is the leaf that is defined by x2 being smaller than 0.03. So this is this first line that was drawn, so this is this node right there. And then the second one is x1 less than or equal to 0.8. So it's this line that was drawn, right? So this leaf, this was the first partition. This is the second partition under this branch. Then in the other branch, you get all of these partitions that happen. So this visualization and that visualization are entirely equivalent. And you see here the value in each leaf. This is just the mean of y within each leaf. And the same way here, you have the mean of y within each leaf that is displayed. So this visualization is also a tree. Unfortunately, you can't really use it if you have more than two variables, whereas this visualization you can use with as many variables as you want. Okay, so now let's try to formalize this a little bit with just some simple equations. So this is really quite simple. If you think of this q being the sum of squared errors yi minus y bar squared, summed over all your observations. So this is what you minimize in a classic regression framework. Now, in this case, instead of just minimizing that, what you're looking for is the kth variable and the c threshold that will minimize the split sum of squared errors. And the split sum of squared errors is just the sum of squared errors in the sample on the left plus the sum of squared errors in the sample on the right. So for every possible variable, if there are k of them, and every possible threshold value c on each of these variables, you have to try this, compute it, and then you find which is the lowest, just like we did a second ago. Now, how do you avoid overfitting? So the first thing we said earlier is that, well, you could ask for a minimum observation per leaf, which would prevent you from going all the way down to just one observation per leaf. So that's good, but it's a little bit crude. There's actually another way that people do this is by adding a penalty. This is kind of similar to what we did when we were doing ridge and lasso and we imposed penalties on the sum of squares. So here we're going to have a tree complexity penalty, which is, for instance, just a linear term, which is alpha times t, where t is the number of leaves in the tree. And so then a tree with smaller amount of leaves or a smaller tree would be more preferred if we choose on QP, Q with a penalty, rather than on simple Q. Now, of course, you're going to ask, how do you actually pick this alpha? Well, as always, you're going to run some cross-validation again. So as you see, we're always running these same algorithms. So this process of avoiding the big trees is called pruning. So for instance, if you go all the way and you make this tree, given your data, this, let's say, is the largest tree that you could make with your data, given some minimum amount of observations within each leaf. You can prune this tree by getting rid of this split. This is the prune tree. Then you can prune this tree back to this one. Then you can prune the tree back to this one. And finally, you can prune it down to just one single leaf tree. Now, mathematically, the sum of squared errors of this tree is greater than this one, which is greater than that one, greater than this one, etc., etc. The bigger tree always has a smaller sum of squared errors. However, with this penalty term, it is not clear which one is smallest, because here we take SSE plus alpha times 5 because there are 5 leaves. Here we take SSE with alpha times 4, so this SSE is larger, but we added a smaller penalty, so we don't know if in total it is larger or smaller. And same thing here, and same thing here, same thing here. So we don't know beforehand which of these will have the smallest penalized SSE. And that's how you might end up picking this tree or that tree or a smaller tree rather than just always the biggest tree. Now, a quick word on the difference between classification and regression. The first key difference is, of course, the nature of your y variable. In classification, your y variable is a categorical variable. So the values of y are not numeric, they are categories, or what machine learning people like to call labels. And of course, since those are labels, you can't really compute a sum of squared errors. You don't really have this concept of distance between whatever prediction you have and the true value of the label. So given that you can't compute a sum of squared errors, you have to find another way to find your optimal tree. And you do that by minimizing something called the Gini impurity index. The Gini impurity index is simply based on the fractions of observations in the leaf that have a given label L. So if you have categories, if you're trying to classify between 5 or 6 or 10 categories, you're going to have 5 or 6 or 10 different P values in each leaf, one for each of the labels, one for each of the categories. And so the Gini specifically is minus PL times log of PL, again where PL is the fraction with label L. Minus because obviously the log of something smaller than 1 is negative. So other than that, the classification and the regression frameworks are the same. You're going to prune classification trees the same way you prune regression trees, etc. And similarly, you're going to turn your classification and your regression trees into forests in the same way. And this leads us to our next topic, which is random forests. The intuition behind random forests is actually quite simple. So obviously they're called forests because they are made from many trees. The intuition is simply that a random forest averages the outcomes over lots of trees. So of course you ask, how do you actually get these many trees? Well, the way you do that is you take a subsample Sj of your data. So instead of taking your full data, you just take a subsample, and then you take a subset of variables, let's say Vj, from your data as well. And then you build the best tree given Sj and Vj. So you take a subsample of your data and you select only some of the variables in your data and you make the best tree. And then you start over taking another subsample of your data and another subsample of your variables and you make the best tree given that. And you do this repeatedly as many times as possible. And each of these tree is going to give a different kind of prediction for each of your possible points. And what you're going to do is take the average of that as your predicted value. Now, why are they called random forests? Well, because the subsample you take is a random bootstrapped subsample, and the subset of variables is also a random subset. And so because you are making a bunch of random trees, we call that a random forest. This figure right here, I think, illustrates this very, very well. It's taken from this article from Athey and Imbens in ARE. What it shows you here is that you can have 3 different trees on the exact same data set. And then if you're thinking about this cross here, this observation, it falls into a different leaf at every point. And what you see is that the other values that surround it sometimes fall together with it in the same leaf. Sometimes it's a slightly different set that fall within it in the same leaf, sometimes it's yet another. And of course, every time the prediction for this observation is going to be based on the mean of those values, or the mean of those values, or the mean of those values. And so the importance of each of the dots in the data set in determining the prediction for this particular uh, data point is going to be proportional to how often it tends to fall inside of the same leaf. So these few observations here are always in the same leaf. Those are only sometimes in the same leaf. Those are only sometimes in the same leaf, etc. So here you can think of this as kind of smoothing the prediction and assigning greater weight to the observations that tend to fall within the same leaf as this one more often. And of course, this is true at every point. And again, this should make you think of how a kernel regression works. So you're going to hear the word ensemble quite often, ensemble methods. Well, random forest can be just seen as an ensemble method. Ensemble methods are just when you take different machine learning algorithms and you average their results together to get your prediction. And by the way, ensemble actually just means together in French. And so in that sense, the random forest is simply an ensemble algorithm using lots of decision trees. That said, of course, you can make an ensemble of ensembles in the sense that random forests themselves can be part of an ensemble strategy where you're using random forests and lasso and ridge and neural networks using some weighted average, right? So you can have an ensemble of ensembles. These methods tend to be very scalable. And by the way, ensemble methods tend to be the ones that perform the best in all these very difficult prediction tasks. I don't know if you've heard of the Netflix challenge, where lots of teams are trying to figure out a way to best predict the movies that somebody is going to like. And apparently, the winning strategies were always ensemble methods. And that's it. Once you understand what a classification tree is, then a random forest is just an ensemble of trees. It's that simple. So now let's look at how we can actually run these algorithms in R. So remember that R is used by lots of people who do machine learning. And so these being the methods that are most popular among the machine learning literature, you're going to have lots of packages that help you do these kinds of things. So there's a method called tree, which we're going to use today. There's one called random forest. You can imagine what both of these do. There's one called rpart, and there's rpart plot that helps you make really nice plots of trees. And most importantly, there's this method called caret, which is a very well-developed package for a lot of different machine learning algorithms, not just trees and forests, actually. But as always, this field is growing fast, and so there are always more algorithms being developed. So let us go back to our y given x example, where we're just trying to predict the value of y given the value of x. Let me just remind you, this was our data, and this is how we had split that into a tree. Now let's see what R does with that. All we need to do is write tree of y given x within this data. And then we ask to see what's inside of tree. There's a bunch of text. It's telling us what the root is. It's telling us something about x being less than 5.5, etc. It gives us a little star telling us that these are the terminal nodes. All of these numbers look quite familiar, but let us look actually graphically. So what we did here is we just plotted our y and our x in the background, and we ask it to overlay with this add equals true command, this partition tree of our tree object. The partition tree is just this red line that shows us the partition, and it is the one that we were expecting, with a first split at 5.5 and a second split here at, I guess, 11.5. So it's finding the same tree that we were expecting. And these tree objects are actually quite convenient. You can plot them. All you need to do is say plot t, and it draws this tree for you. And all you need to do then to overlay the text on top of that is to say text of t, and it knows what to do. It knows to add the values here. And so this tree is exactly the one that we had done by hand earlier. The values here are slightly different, but the decisions are actually the same. Okay, so now what would this look like if we had two x variables trying to predict our y variable? So remember the iris dataset. That's the dataset where we had dimensions of flowers by species. The species is here, species of iris, setosa, and I can't remember what the others are. And here we have four variables: sepal length, sepal width, petal length, and petal width. Let's just forget about one of these right now. Let's forget about petal width. Let's just do, we're predicting petal length on the dimensions of the sepals, sepal length and sepal width. So again, all we have to do is just run the tree command on this y variable, of this y variable on these two x variables. We create this object called iris tree, and then we can just plot our three variables, or should I say we can plot the space defined by our two x variables. So this is one of our x variables. This is our second x variable. Here, the value of y is determined by the color. Okay, the color is the petal length. And over that graph, we can overlay this partition tree based on our tree object, right? And so the partition tree are these lines here that define a partition of our x variable space. And again, it's a full partition of the x variable space. And what do we see? Well, we see that this tree did a pretty good job at recognizing that there are a bunch of low values here with a mean of 1.53. They are in black. Here there are a bunch of relatively high values. They're in pink and they have 6.3 as a mean. And here in between, it kind of tries to recognize bunches. Here's some green values, here's some blue values, light blue, dark blue. The tree is doing a relatively good job at recognizing kind of homogeneous zones of this covariate space. If we look at it as a tree, again, all we need to do is run plot of this tree object, and it tells us that this is how it would split the sample into successive leaves to get fairly homogeneous leaves in the end. Okay, so now let's do something a little bit more complicated. Let's try to see if we can predict the price of a car. So there's a data set that comes preloaded with the Caret package, which is a package that is used a lot by machine learning, or is used a lot to run machine learning algorithms. So it gives us 800 observations of prices of cars taken straight from the Kelley Blue Book. So here's just what this looks like. It's a data set of the price, there's the mileage of the car, and then the number of cylinders, the number of doors, some things about cruise control, etc., whether it has leather seats, and then just a bunch of dummies for different brands, and a bunch of dummies for different styles, convertible, coupe, etc. Okay, so let us first do this as an OLS, which would be kind of the first step of things that an economist would do if we were trying to find the factors that explain the price of a car. So we run a simple regression command, lm, we call it price OLS. Here is a truncated view of the output. We see that, of course, the mileage matters, the cylinder matters, etc., etc. We're not that interested in the coefficients. What we're interested is in knowing whether the predictions worked very well or not. One way to look at that is to think about the R squared. So we look at the adjusted R squared for our price OLS model, and it's 0.91. So 91% of the variation in price is explained by our model, and this is the adjusted R squared. So we're already taking into account the fact that we've been using some more variables, right? Okay, let's pit this against a tree. Now we just run again the exact same specification, price against all of the other variables, but now instead of a linear model, we fit a tree instead. So again, this is a truncated output. We don't want to look at that. What we want to look at is the tree. So the tree has some decision rules that might seem kind of obscure. The root is whether or not the number of cylinders is less than or greater than 7. Then in the next branch, the most important, the critical variable became whether or not it's a SOB, et cetera, et cetera. Then cylinders again. So all of this is kind of obscure and unclear why those are the variables that work best, but those are the variables that work best. And here in each leaf, you get a prediction of what the price of a car that satisfies these conditions might be. So let's see in terms of prediction how well these two models do. So we have our predictions of OLS. We just get them by running predict and the name of the model. Same thing with the tree, predict with a tree model. So we make a little data frame with both of our predictions, and we're going to make a ggplot. Let's first start with a plot that only has the actual price of the car and the OLS predicted price of the car. So if we look at that plot, this is what it looks like. In blue, we have this OLS line. These are all of the predictions of our prices. And here in black in the background, the black background, those are the actual prices. So two things here. First of all, indeed, we see a relatively okay prediction. The trend is fairly clear. In terms of a linear regression, this is not doing too bad, right? Except here it's a little bit far off, here it's a little bit far off, but overall, we like this quite a bit. Now let's take that plot and add the tree predictions. They're going to be in green, of course. So what do we see here? First of all, the tree predictions are all like these straight lines. Why are they straight lines like that? Well, remember, the tree gives the same prediction value to all of the observations within one leaf. So here apparently it found some variables that it put into a leaf, and this is the prediction, which is the mean of all of these observations. They all get the same prediction value. Here's another leaf, here's another leaf, here's another leaf, etc. So you can see where the leaves are. And when you look at it that way, well, this looks a bit crude. If just visually, we might say, okay, the OLS seems like it's capturing this trend a little bit better. It seems visually a little bit more appealing. That said, notice that some of these leaves seem to be capturing features of this data set that the OLS is not capturing. So for instance, up here, obviously the OLS is clearly below, and this, even though it is a crude approximation, this might actually be a better approximation within this group, right? Same thing here, this leaf might be a little bit better at capturing these observations. This leaf might be a little bit better at capturing these observations, etc. So which one would be preferred here? It's unclear at this point. So let us look at the mean squared errors of these two prediction models. We just run this command called MSE. So we run the mean squared errors between the OLS predicted values and the real price, and the mean squared errors between the tree predicted errors and the actual price. And here we do a little bar plot. The OLS actually has slightly lower mean squared error than the tree. So right now the tree is not doing a better job than the OLS, but that's precisely why we have forests. So let us now run the same model using the random forest command. Again, it's price against all of the other variables using random forest. We call this object price underscore RF. Here's the output. It's telling us that it used 500 different trees, and that within each split, it used 5 variables. So remember, it's using only a subset of variables in each of the random trees, and the number of variables is 5. This is an option that you can change. Again, we compute the predictions from the random forest, and we add it to our plot. This time it's going to be in red. And here what do we see? Well, the predictions out of the forest are much, much more flexible than either the predictions of the OLS, which are just a straight line, or the predictions of the single tree, which are these flat leaves here, or flat lines corresponding each to a leaf. Here with the random forest, you can see that the predictions are much, much more dispersed here and seem to be catching the features of the data a little bit better. So the question is, do we see that with the mean squared errors? Well, yes, it's actually quite clear. If we can compute the mean squared error between the random forest predicted values and the actual prices, the random forest one is much lower than the mean squared error of the tree or of the OLS. So this kind of shows you why random forests have been so popular and why they've been so good at helping us with predictions, because they are so flexible. They are able to flexibly capture all of the different idiosyncrasies of your data. Of course, we only used relatively simple models. Here we can make more complex linear models that would probably predict the data better. However, of course, the random forest, also there exists more complicated random forest models that can help us with the data. So overall, random forests have been very, very powerful in the realm of predictions. So for those of you who want to dig deeper in those topics, the next few slides should help you with that. So first of all, as you dig into this literature, you're going to realize that most of the vocabulary is very different from what we use as economists. So some machine learning vocabulary that you should be familiar with. First thing is, when we say variable, the machine learning people usually say features, except for the y variable. The y variable is usually not called a feature, but all of the covariates are called features. The second thing you should be familiar with is this notion of training versus testing. I didn't use this at all in either this lecture or the previous lecture, because in fact, it's not necessary for explaining how the models work. However, the mechanics of how you do predictions usually involve splitting your sample into a training sample and a testing sample. This is what most machine learning people do. The point is that you take a first subsample where you estimate your model, and then you take the rest subsample that you did not touch before, and you test whether your model performs well in that other subsample or not. We've talked about these kinds of techniques a lot when we talked about cross-validation and k-fold sampling and bootstrapping, etc. All of that relies on taking some of your data and leaving some of your data out. Notice that also the ML literature is going to say the word training when we say estimating. And lastly, be careful because usually these algorithms involve splitting the sample multiple times. So you might split the sample once into training and testing, and then within the training dataset, you're also splitting because you're doing some k-folds validation or some bootstrapping, etc. Which brings us to the next word, the word bagging. So bagging just means bootstrap aggregation. So this just means you take bootstrapped samples of your original sample and you aggregate the results at the end. And every time you do that, you might test the performance of your model inside of the sample that is left over, that is outside of your bootstrap. So the sample that is left over from your bootstrap, that is called the out of bag sample, or OOB. So one thing you'll notice is that when you're reading these machine learning papers, a lot of what people are saying might seem daunting and hard to understand, but actually they map very clearly to things that we talk about all the time. So if you just get used to this slightly different vocabulary, it should demystify a lot of this literature fairly quickly. Another thing you should really look into if you want to dig deeper into these kinds of methods is the CARET package. Now, the CARET package stands for Classification and Regression Training. So again, training, what does it mean? It means estimating. So it's a package that estimates a lot of different models. And it does a lot of different things for you. It can, for instance, it pre-processes the data. And with big data sets, it can pre-process all of your variables in ways that really save some time. It also does the splitting between training and testing data. It does the random splits in any possible way that you might want. It does all of the cross validations and the bagging and all of that stuff. And in fact, it goes far beyond just trees and forests. You can use it to do neural networks, support vector machines, etc., lasso, and all that. It's a kind of a full, complete machine learning package that a lot of people use. So this is probably your next step if you want to dig deeper into those methodologies in practical terms. Following on that, how would we actually use those methodologies in economics? Well, there are several things. First of all, there are some prediction problems that are very policy relevant. So you might be able to write economics papers just based on predictions rather than on inference. The second class of applications are, of course, the causal inference methods that do have an embedded prediction stage inside of them. So I already talked about that last week. For instance, when we do matching methods, matching methods are often prediction methods. So the matching stage, instead of using a discrete choice model, we might use one of these machine learning methodologies now. There is a relatively novel methodology referred to as causal trees. So what are causal trees? That's just when you use a tree to partition your data in an optimal way, and then you do causal inference within the partition that is created by your tree. So this is to identify heterogeneous treatment effects, and it's a way to combine kind of the power of the tree algorithms with the power of our causal inference algorithms. And finally, this has been pushed a little further by Wager and Athey as causal forests, and you can look out this paper from a couple of years ago that shows you that. If you're interested in further reading on these topics, of course, pretty much anything that's been written by Susan Athey within the recent years is going to be on your reading list. So there's this paper in 2018 about generalized random forest. There's this paper that is called Beyond Prediction, how we can use big data for policy issues. And I also really recommend
And this paper from 2018, The Impact of Machine Learning on Economics, that explains quite a lot of this stuff. And of course, even though Susan Athey is the one who's written most about all these things, there are also a few papers written by other people than herself. You can look inside of the reference sections in all of these papers. She references some of those. But currently, everybody is looking into these methodologies, so very likely in the next 5 years, we're going to have an explosion of literature about these topics, both in the theoretical and in the applied literature. Finally, if you're really interested in kind of getting some hands-on practice with machine learning methodologies, I strongly suggest that you sign up for Kaggle competitions or just go to the Kaggle website. Kaggle competitions use real-world problems. They provide you with actual real data and they try to crowdsource a solution. So teams around the world, anyone who signed up on the website, can take the data and try prediction algorithms, and whoever gets the best prediction wins something. The really difficult problems that are sponsored by companies actually have financial gain at the end. But in addition to these big, difficult projects that are actually sponsored by private entities and that actually have financial prizes at the end, there's also a lot of very good training materials. You can do these kind of very tiny competitions where there's actually no more competition, they're just for training. And so you can test yourself and you can learn a lot just by doing these. And that's it. Thank you so much for listening.